Hello, today it's my pleasure to talk about general regression. So earlier we did a video on linear regression and power regression. So I want to make sure you watch that before you watch this one. So what is regression? This is when you fit a curve to some data. The curve's not a perfect fit. Not all data points will pass through the curve. In fact, most probably won't. Here's an example of what we did in the previous example, or the previous video. We had some data, and then we tried to fit a line through it the best we could. So this particular example of a linear fit, that's like a polynomial. What we're going to move to today is polynomial regression. That is like a polynomial first degree, obviously, and or if you have multivariate linear, the example here was a single or a univariate linear type of regression. And then what we're going to do is try to unify everything to give it kind of a consistent look, and then we'll finish up with a multivariate power model. Okay. So here we go. So far in our previous video, we were thinking about being given some y values, for example, n data points of that. And we could talk about the average of those being the sum of those y's divided by the number of data points that we had. And then we entered into residuals. The residuals would be the data minus the mean or the average. Take that and then you square it, and then the sum of the squares of residuals would be what we called S sub t. So sum of the squares of residuals, that's a big metric that we worked on. A standard deviation is where we take the sum of squares of residuals and divide by n minus 1, and then take the square root. So why n minus 1 and not n? We talked about that. It's because there's an n minus 1 degrees of freedom once you establish what the mean is and using that as a reference. Okay, and then the next thing we did is looking at a linear regression of a single variable where you're given some x values, n of them, and you try to fit that line where you're looking for the y-intercept and then the slope. And then you set up a different look for residuals. So this is sum of squares of residuals for the line fit. And then there's a standard error that takes that sum of squares of residuals and divided by n by minus 2, since you've lost 2 degrees of freedom due to having those coefficients. And then there was a power model that we worked on where we looked at taking the data, raising it to a particular power, and then scaling it. So that was a little bit different. We used a log-log plot to effectively show that the power model is the same as a linear fit. Okay, so that's what we did in the previous video. And then we established some terminology. Coefficient of determination is where the ST, the average, the coefficient, the sum of squares of residuals with respect to the mean minus the sum of squares of residuals relative to the line. You take that difference and divide by the one for the mean, and that's going to be a coefficient of determination, r squared. You have a similar one for the power model, and then the correlation coefficients would simply be the square roots of those. So this was a big metric here that we used previously. It's important to go back and look at the linear regression to put some perspective on that. Remember that we're looking at the sum of squares of residuals, and we're interested in taking that function and minimizing it. We want to be able to choose the A0 and the A1 such that the SR is minimized. Well, hell, that's just the derivatives. You take the two derivatives, so they're going to be partials. You take those, you set those equal to 0. You're given the xi and the yi. So it ends up being that these two equations transition into something that looks like this. And that was, quite frankly, the basis once we solved these equations for A0 and A1. They're actually two linear equations and two unknowns. So very easy for us to use our linear algebra to solve for A0 and A1. And then we extended it to a power model where we did this in a log-log space. So very much the same thing. Okay, so what I want to do is take that, what we talked about before, where we're looking at discrete linear equations here, take those discrete linear equations and transition it into a full matrix equation type of thing. And it's going to be over-determined the way I'm laying this out. So we have A0 and A1. Those are our unknowns. Our y data, that's going to be our knowns. That's going to be our B column. The A0s and A1, that forms an A column. And then I'm going to look for a Z matrix. I'm going to call it capital Z, and it's going to have a column of ones, and it's going to have a column of x's. So this is going to be actually an n by 2 matrix. This will be a 2 by 1, and this will be an n by 1. So it's what they call overdetermined set of linear equations. Okay, so the Z matrix is not square, so you can't just simply invert that since it's not square. So what we can do, though, is we can take Z transpose and multiply both sides of this equation by Z transpose. So we'll have Z transpose Z on the left, and we'll have Z transpose B on the right. And then the Z transpose Z is going to be 2 by 2, and we're going to be able to invert that. Typically would be able to invert that. So in that case, we're going to be solving for our A, our unknown A column matrix, which is going to be 2 by 1, in this case A0 and A1, and that's going to be equal to that Z transpose Z inverse times Z transpose times B. So how does this work? Why does this work? Well, to be honest, the right hand, the Z transpose B, is effectively going to give you that summation of yi, summation of xi, yi. If we go back and look at what the side over here, so that's going to give you this, effectively going to give you that. Okay, so, and then the left-hand side, the Z transpose Z, that's going to give you the 2 by 2 matrix that's n. It's going to have a summation of x sub I along the anti-diagonal, and it's going to have a summation of x sub I squared in that bottom right element of that 2 by 2. If you go back and look at what the original system will look like, so we're talking about this end, the summation of x sub I, and the summation of x sub I squared. So that's why it works. It's a very easy way to implement the linear least squared fit to give you that linear regression. And what I thought I would do is refresh your memory on this, how we got that line that had an A0 of minus 234, and then it had a slope of 19.47. And that was all based on taking these individual columns and looking at the summation and putting those elements into the solution equation. So what we can do now is we can replicate that. So I've shown you this code earlier, and now what I want to do is show you how to get that Z, the Z matrix. And how I build the Z is actually I build the transpose. It's quite easy to build the transpose, and then you transpose it, and now you have your Z. So I do this replicate matrix, repmat in MATLAB. I just replicate a 1, and I make it into a 1 by n row vector, and then I do a semicolon, so that means in the row, start the next row, concatenate that x, and the x is coming in as a row. So I've got my Z transpose, and then I just do a tick on it to give myself the Z. The y coming in was as a row, so I'm going to take my my prime or my transpose. The tick is the transpose operator. So now B is a column, and then I implement the inverse of Z transpose Z times Z transpose B, and then I look at the code. The A1 and the A0 are the brute force way that we had learned earlier. And then the A alternate here, that's going to be the result of that matrix multiplication. So this is a much more compact way of doing it, and it extends, as I'm going to show you now, it extends into polynomial regression as well as multivariate regression. It extends very nicely. Okay, so for polynomial regression, I'm going to kind of try to get you thinking in terms of an example where we're looking to fit a naught a1 times x plus an a2. So we're adding a term, a2x squared. So we're going to make it a polynomial now. And you can tell this data is contrived because a line's not going to be a good fit, yet that parabola would be a nice fit there. Okay, so we take this this y that looks like a parabolic equation, and we set up our residuals for that. So the residual is going to be sum squared of the yi minus the fit quantity squared, some of those, the sum of squares of the residuals. So that's going to be my SR. And then I'm going to do the same thing. I'm going to differentiate that because I'm interested in finding the A0, A1, and A2 that minimizes that SR. And when I do that, I set each of those equations equal to 0 and end up with just an expanded, quite frankly, an expanded version of what I had earlier with just a linear regression. So what I can do now, so this is the m equals 2. So the m is sort of tracking the degree of the polynomial. N is the number of data points. But at the end of the day, you're going to get m plus 1 linear equations. So previously, we were talking about a line, so m is 1. So we had 2 linear equations and 2 unknowns. Now for this one, for the parabola, m is 2, so we're going to have 3 equations and 3 unknowns, where we're adding the a2 as an unknown. Standard error is similar to taking what we had for the linear regression. We have SR divided by n minus m plus quantity m plus 1, and square root of that. Okay, so here we're going to look at multivariate or multiple linear regression, where we have 2 x values. We have an x1, we have an x2. So in this situation, we're kind of looking for a best plane fit. Is it, if you're talking about two multivariates, you've got x1 and x2. When you have 2, then you're looking at a plane instead of a line. You're looking at a best plane fit, and that would be the y equals a0 plus a1 x1 plus a2 x2. So that's our fit that we're looking at. So our sum of squares of residuals would look like this, and same thing. We're interested in what a0, a1, and a2 makes that SR minimum, and you're just going to look at partial derivatives set equal to 0, and you're going to get, really an extension of what we had on the linear version, the linear regression version of this. So same kind of thing as we have with polynomial, quite frankly. Just here, everything is linear, just have multiple variables. Standard error, similar. Okay, so what I like to do now is kind of think about a general regression where, you just kind of tweak it to make it look like a linear, multilinear, or polynomial, just depending on the context of it. So I came up with this idea of using where we're looking for the a0, a1, a2, etc., all the way to am, and we're given as the data points. We're given, I just call them little z's, z0, z1, z2, up to zm. And if it's a linear or multilinear type of situation, the z0 is going to be 1. So it kind of makes it nice, and every term here looks the same. So that's why I could have just, because the z0 for polynomial is going to be 1 as well, but just kind of trying to make everything look consistent. So for linear, multilinear, z0 is 1. Z1 is going to be my x1. Z2 is going to be my x2. And all the way up to, if I have m, zm is going to be the mth x data point. If it's a polynomial, instead, trying to fit a polynomial to some data, then again, my z0 is 1. My z1 is going to be my x. My z2 is going to be x squared. So, and then the z, whatever z I end up with, the zm is going to be x to the m power. Okay, and then sum of squares of residuals, just generically, is going to look like this. Okay. And you end up basically, when you kind of multiply it out, you end up with each data point that you have is going to be the a0 times the associated z0 I. It's always going to be 1 for that. And then a1 is going to be the z1 data point I. So it could be the first x, or it could be x if it's a polynomial. The z2i is going to be the second x, the first one of the second x coordinate, or it's going to be the x squared if it's a polynomial, and so forth. And then the e is going to be just whatever the residual is for that particular y data point. So what I want to do is I want to get it into a kind of a generic way of building my capital Z matrix. So I've got my capital Z, I've got some A0, A1 up to AM coefficients that I'm hoping to find. I've got my Y data points that I'm given. And whatever goes in here is based on the X, whatever the associated X data point would be. E is your residuals. So here it is. Here's kind of the way you do it. You're going to create a linear system with the unknown A's. You're going to have your Z is going to be overdetermined, so you multiply both sides by Z transpose, and then you can invert it. So you would end up with, here would be an n plus 1 by n plus 1 matrix that you can invert. And over here, you would have an n plus 1 by n matrix after you transpose it, and then y is going to be an n by 1. So this is exactly what we're going to be looking for. So let's put it to good use here. Here's an example. So here's a parabola example that we're fitting data to, and we could use a brute force way, where we build this type of thing. And then we invert it. So that's what the book showed you, but I'm going to show you my Z matrix, Z method here, and show you that it's the same. So here's what I did is I put together my data. So the X data is just 0 through 5, and then the Y data associated 2.1, 7.7 up to 61.1. 2.1, 7.7, 61.1. So I've got my Y data squared away, figure out what my length is. And then here, as I say, I build it based on the transpose of Z, because it's much easier. So I replicate a matrix, a row of ones that is n long. And then I end it with a semicolon. I bring my X in as a second row. And then remember the x dot caret 2 is going to take each of the x's. That's a element-wise exponent of 2, each of the x's, and square them. So I'd get a third row that's going to be my each of my x's squared. And then I get my z by just taking that z transpose, zt, and transposing it. The y came in is given as a row. So I get my b by transposing that to a column. And then here's my A alts. I basically just took what I did in the previous linear example, same code really. And then I get my Y fit as Z times A alternate. And then I went ahead, now that's going to be a column. I went ahead and made it like a row by row, so that I could figure out how that fit relates. So I could go Y minus Y fit, each one squared, and then I sum them. So that's going to be the sum of squares of residuals for my fitted data, the parabola. And this is going to be the sum of squares of the data relative to the mean. And there's how good it is. So here we go. So, and then I plot it. So here we go. I got the A alternate, so 2.4785 for my A naught, 2.4786, and then for my A1, 2.3592, 93, 2.3593, and then for my A2, I got 1.8607, 1.8. So got the same results. There's that polynomial, the parabola, all right? And the r squared looks like it's a 0.9985. R squared 0.9985. So yay, verily, this method works very well. And this particular example, we've done very well. Remember, if r squared is 1, that's a perfect. So the data is very, very close. The polynomial fit is very, very close to the original data. And there's how it looks. You can see it, that the polynomial fits the data pretty well. So that's polynomial regression. Multiple linear regression. Okay, we're interested in figuring out A0, A1, and A2. That takes this given data, the X1, X2 data, and fits it to this Y data that we're also given. So they go through a number, just taking the sums of each of these particular columns and then putting them together in this way and solving the equation for A0, A1, and A2. And they got A0 is 5, A1 is 4, A2 is -3. So that this is like a red flag for me, that a little bit of a contrived example. That's okay. So we want to show that, yes, our data, so it must mean that the data fits through it perfectly. Let's see. So I took the data that they gave me, the O2, 2.5, 147, O2 2.5 to O2, 2.5, 147, and my X2 is 012362, 012362. My Y data is 510, 90327, 510, 903. Okay, so I've replicated that well. I got my N is the number of data points. And then I go through with my matrix form. Remember, I build it by ZT, Z transpose. So I go that row of ones, that's N wide. And then I concatenate X1 as the second row, X2 is the third row. All right, then I go ahead and get my transpose like that. Y is coming in as a row vector, so I set myself up for B being a column vector, and then I just do my handy dandy inverse of Z transpose Z times Z transpose times B. And then I can do my fit, and then I can do, well, how good was the fit? Okay, and then looking at the results, my I think they were getting like 5, 4, -3. So essentially I got 5. I printed it all the way to 16th decimal place. And so essentially 5, 4, and -3. So I got the same thing. The ST is 458. Look at the SR. So it is effectively, it is 0. So my R2 ends up being 1, which says that multivariate or multilinear regression was a perfect improvement, perfect fit. Okay, so we could take that information that we did earlier, how we did the linear and extended that to a power model. We could do that for a multivariate power model. So we would have an A0, and then each of the x's, however many we had, we would have a particular exponent for those. So then when we think about, the logarithmic sort of identities that we have, we could express it in terms of sum of logs, where we have an offset, and then we have that exponent's coming down to scale the particular log, associated log. So these are log 10. Typically we deal with decades, so that's what that is. So you could very easily extend this problem that this technique that we've just learned. Okay, so So I wanted to go in this presentation. I wanted to collect our thoughts on earlier regressions where we did linear and power, and see how we can kind of extend extend that to polynomial regression and then multivariate regression. Then we kind of unified it into the general, which could apply to anything, and then we extended it to the multivariate by discussion. So anyway, so that's all for today. I hope you've enjoyed it.